Hi, in this module we'll be discussing experimental design in fMRI. Let's just recap where we are so far. In the first couple of modules we've talked about data acquisition and reconstruction. Right now we're going to talk about experimental design for a while, and then we're going to move into pre-processing in the next couple of modules. So the goals of experimental design in fMRI are: 1, to induce subjects to perform or experience the psychological states that you want to study, and 2, to be able to effectively detect the brain signals related to these psychological states. This is not always so easy in practice, and both psychological and statistical considerations will always need to be taken into consideration. The psychological considerations are related to inducing the subject to experience what you want them to experience, and the statistical considerations are involved with being able to detect that. Some of the properties of the bold signal really kind of conspire to make experimental design difficult in fMRI. Now, we've already seen that the signal is both weak and noisy, but also we've seen that it's not an absolute measure of neuronal activation. So when we measure bold response, we're not getting an absolute measure of the neural activity in the brain, we're getting an indirect measure through the oxygen consumption. So in order to make conclusions, we really need to use contrasts and repetitions to be able to detect effects of interest. So the contrasts are needed because we need to be able to compare the task of interest with some control task where the subjects are either at rest or performing some simple baseline task. And second, because of the weakness of the signal, we have to repeat the task as often as possible so that we can get bigger signal to noise ratio. Okay, let's start with some definitions. An event is a single experimental manipulation. It could be something like viewing a picture or clapping your hands or whatnot. The interstimulus interval, or the ISI, is the time between two successive stimuli. So if you have an event 1 where you're viewing one picture and event 2 where you're viewing a second picture, the time between those two viewings is the ISI. Now, a block is a time interval that contains events from a single condition. So let's say that you're looking at pictures of famous faces versus pictures of non-famous faces. A block would be a series of images of famous faces that are shown one after the other. So there's two main types of experimental design that we use in fMRI. The first is what's called a block design. Here, similar events are grouped together. So if we have two conditions, A and B, we would have A for 20 seconds in this example, B for 20 seconds, A for 20 seconds, B for 20 seconds. The contrast that we would be interested in looking at would be the difference between the signal during condition A versus during condition B. Now, these type of block designs tend to have high statistical power to detect activation and are robust to uncertainties in the shape of the hemodynamic response function, or the HRF. However, they're not very good at directly estimating features of the HRF. Now let's take a look back at this linear time invariant system example from a previous module. We see that if we have a block design like this, here let's say that one of the conditions is rest and condition B is some task, finger tapping. If we were to convolve this experimental paradigm with the hemodynamic response function, we get this green function at the bottom here. And this green function is very robust. There's a very strong difference between the resting condition in amplitude and the finger tapping condition. And so this is a very strong signal that we should be able to detect. However, if we, for example, let's look at this from a different angle. Let's say that we have this measured bold response and we know the experimental stimulus function. If we instead we assume that we don't know what the hemodynamic response function looks like and we want to estimate that, then this type of design is not very efficient for doing that. And we'll see a lot more of this as we move along. Event-related designs, here the events are mixed. So you have condition A and condition B that are given intermixed with each other. So in the example of, say, famous versus non-famous faces, you would show a famous face, a non-famous face, maybe two famous faces, a non-famous face, etc. Now these types of designs tend to allow for very efficient estimation of features of the HRF. So they're good for HRF estimation. However, they provide decreased power to detect activation. So if we look at the similar kind of cartoon for event-related designs, we see that difference between baseline and rest is less defined here. However, these types of things, as we'll see again later on, are going to be very efficient for estimating the HRF. The next thing we have to take into consideration here are the psychological considerations. So basically, if we want to study a certain psychological state, we have to make sure that the subject are actually experiencing that state. So it's important that the task induces the subject to think or perform in the manner that we intend. So there's a lot of things that we have to take into consideration. The first is that you don't want to make the study too predictable, as this might influence the subject's psychological state. Now, for example, if you have a task where you see letters and you're supposed to press a button every time you see a letter, but not when you see a certain letter, say X. So this is a type of go, no-go task. If you have a long series of X's in a row, it becomes much easier to not press the button. However, if the X's are intermixed with lots of other types of letters, it becomes harder. So here you want to keep the task as unpredictable as possible to make sure that the subjects are in the proper state. Second thing is we need to make sure to keep subjects on task by giving them just about the right amount of time to perform the task. For example, if we have the famous versus non-famous faces type of task, if we let the people look at the pictures, people recognize images or famous faces very, very quickly. And if you give them too much time to think about these, you might think about, your mind might start wandering and you start thinking about other things, and you're kind of getting away from what the task is, which is to see whether or not you recognize the picture, yes or no. The third thing is you have to make sure that different stimuli configurations don't afford different strategies. So it might be if you have certain stimuli in a certain order, you can perform the task in one manner, but while if you have them in a different order, you can use a different strategy to solve the problem. And that's no good, because then you're imaging two different types of psychological states. Fourth, what you expect from the subjects should really be able to fit with what they can actually do. Here, let's say that you want to compare the recall of sad memories versus the recall of happy memories. In general, a typical fMRI block designs won't work very well here because subjects just can't switch back and forth among emotions that easily. So feeling states take longer to achieve, and they don't go away when you want to turn them off. So you can't turn off being happy and then being sad, being happy, being sad in that type of manner. So that's kind of a hard thing for a subject to do, and it's hard to kind of perform an experiment of that type. Also, finally, it's always important that you keep in mind that subjects' brains may be responding to things that you didn't tell them to do. So there might be something about the experiment that causes them to respond differently than what you would anticipate. Now, of course, there's lots of different statistical considerations, and we're going to be exploring this throughout the class. But in general, a take-home point is that block designs typically yield high experimental power, but they provide rather imprecise information about the particular psychological process that activate the brain region. On the other hand, event-related designs allow your brain activation to be related more precisely to the particular cognitive process engaged in a certain type of trial. But again, as we said before, they suffer from decreased power. So here are 5 guidelines for designing an fMRI experiment, courtesy of my colleague Tor Wager. The first is you should scan as many subjects as possible. You should scan as long as you can, considering psychological effects such as fatigue and habituation, because you can't keep a person in a scanner too long because they get very tired, and habituation is if they get too used to performing the task, they might perform it in a different manner. The second is you should use short blocks, less than 40 seconds, if you care about detecting differences between condition A and condition B. And you should use event-related designs if you want to link activity to particular events. The third rule is that you should limit the number of conditions. So if you have 8 different conditions, you might have pairwise comparisons that are really, really far apart in time because you have to fit in all 8 conditions. So if you're comparing the 8th condition with the first one, there might be, say, 2 minutes apart. And then you're going to have problems with things like drift, like we talked about last time. So the drift might actually dwarf the difference between first and the 8th condition in this example. Fourth, in event-related designs, you should randomize the order of events that are close together in time, because you don't want things to be too predictable. And you should also randomize intervals between events that need to be distinguished from one another. So you shouldn't always have 5 seconds between events. You should randomize it. That's sometimes called jittering. So these are 5 good rules to use when you're designing your fMRI experiment. If you know something in advance about your statistical model that you're going to use, then you can actually tailor the design to minimize the variance of certain parameter estimates. And there exists computer-aided design algorithms for doing this, and they're based on things like the M sequences or the genetic algorithm. So we might return to this later on after we've talked a little bit about various statistical models. Okay, that's the end of this module, where we've talked about experimental design. Now this is a big topic and we've just scratched the surface on it, but we have what we need to move along. So we've talked about event-related designs and block designs, and we've talked about the fact that we usually have multiple conditions and we look at contrast between conditions, and also that we have lots of replications in order to increase signal-to-noise ratio. So in the next couple of modules we'll be talking about pre-processing, and then we'll be ready for some statistical analysis. Okay, see you next time. Bye.